Good morning, everyone. I welcome all of you to the second day of PyCon US 2022. Let's welcome Chris to deliver a talk on employing NumPy's NPY format for faster-than-Parquet DataFrame serialization. Over to you, Chris.
Thank you. Thank you. Good morning, and thank you all for coming. So, a little bit about me to begin. I am CTO at Research Affiliates. This is a finance firm located in Newport Beach, California. I've been a Python programmer since the year 2000, and my earliest work was in music. I have a PhD in music, and I was a former professor of music technology. And I found lots of ways to use Python in all sorts of different things like algorithmic composition and computational musicology. In the last 10 years, I've been working on financial systems in Python, and that's led me to create an alternative data frame library called StaticFrame. StaticFrame is based on an immutable data model, a more consistent interface than Pandas, and support for all NumPy dtypes, including Unicode strings, datetime 64 units as well. All right, so as over those 10 years building financial systems, many of you might be able to relate to a sort of quest to find a complete DataFrame serialization format. And we've tried many things from CSV, XLS, X, HDF5. Most recently, Parquet has offered the best performance and type retention. But it's not perfect, and no format supports all components of a data frame, and none support all NumPy dtypes. So if a data frame in Python can be thought of as a collection of NumPy arrays, what is the best way to serialize a NumPy array? Well, for that, we can go way back to 2007, to NumPy Enhancement Proposal number 1. Now, similar to PEPs, NEPs are proposals to enhance NumPy, and this one was proposed by Robert Kern in 2007. It defines two things. It defines the NPY file, which is a binary file format that can encode all NumPy arrays, and the NPZ, which is simply a zip bundle of NPY files. Now, this format is still supported in NumPy. You can use it right now with np.save, np.load. What's really interesting about these NPY files is we can memory map array data with them, and that's something we're going to explore with DataFrames later on. So, can a data frame then be serialized as a collection of NPY files? That was sort of my first question. And so I set off to do this. The way I first approached it was simply taking all the arrays that are included within a data frame, package them up with an NPZ. And my first implementation was using npsave and np.load. In addition, I created a special metadata file in JSON that I packed into that NPZ to help me fully reconstruct the data frame. And this worked, but it was slower than Parquet, which was a little disappointing. Looking into the performance of the NumPy routines, I found that if I re-implemented the NPY and NPZ authoring routines, I was able to get massive performance improvements and end up with something faster than Parquet. So I'll give you a little taste of that performance. If we use Pandas here to create a very simple frame of 10,000 square floats, and we create a data frame with that, we're going to write this out as Parquet, but because Parquet requires that all column labels be strings, we're going to have to convert those column labels to strings. And then we can go ahead and use Pandas to write this data frame out as a Parquet file. And that takes about 10.5 seconds. Now, if we build a corresponding frame in StaticFrame, and we export it, we write it out as an NPZ, that takes 1.42 seconds, nearly an order of magnitude better performance for writing out this very, very simple frame. What about reading? Well, we can read in that same Parquet, again, using Pandas, reading in that Parquet file, we can read it into a Pandas data frame in about 5 seconds. If we do the same thing from an NPZ using StaticFrame, we can do it in about 1 second. Not an order of magnitude, but a very significant improvement. All right, so what we're going to do today is we're going to look at the components of a data frame in detail. We're going to look at the NPY and NPZ format to get a sense of how we can use these. We're going to talk about how we encode a data frame in an NPZ. We'll talk about a few of the things I did to improve NPY performance. We'll look at some very thorough performance comparisons. And finally, we'll close by talking about how we can use the NPY now to actually memory map a complete data frame. After this presentation, I hope you gain a clear understanding of data frames and how they're built. You'll also understand NPY encoding, and you'll leave here with more options for serializing and memory mapping data frames. So let's look at the components of a data frame in depth. Now, the first data frame was introduced back in 1991 as part of the S language. They've been around for a long time, and many libraries and many languages have implemented data frames. There is really no standard for a data frame, but what I'm going to provide for you is how StaticFrame defines a frame, and you can think of this as a slight superset over the pandas data frame. So many of you probably worked with data frames, but it's important to remember what they are. They are not a two-dimensional array. A two-dimensional array has uniform type and access to rows and columns only by integer. With a data frame, we get the opportunity to have a table of columnar data where columns have heterogeneous types. And we can label our rows and columns and access them with things other than integers. Our labels can be any type, our labels can be hierarchical, and those hierarchical depths themselves can have different types. In addition, data frames have name attributes attached to the rows, the columns, and the frame itself. And these name attributes give us a really convenient way to either have an additional label or rich metadata attached to those components. Now, I created this schematic diagram of a data frame to help us talk through how we are going to encode this entire data frame. And what I'm showing here are the array components in gray rectangles, the array types in the gray diamonds. The black diamonds are the component types for the index and the columns, and the black circles are the component names for columns, index, and the frame itself. Now, we're going to see this a lot, so I'll help you understand it as we go. But before we do that, I want to compare that representation to the representation of StaticFrame's standard repr of a data frame. You'll notice this is a richer representation than Panda's representation of a data frame, because in StaticFrame, we're very concerned about our types. We want to always show our users what types we have at hand. And I'm going to relate this representation to what we were looking at previously. So here I've highlighted in orange and yellow the values of the data frame. So we can think of this as 4, or actually 2 arrays of first integers and then booleans. This is the data in our data frame, and we can see it in both representations here. In blue-gray here, I'm showing the arrays of the columns, and we can see that we have 2 arrays that represent the columns in this case, hierarchical columns. I have 2 arrays also representing the index here. And then finally, in purple, I have the additional stuff, the types of the index and the columns and the name attributes. And if we bring that all together, you can see the correspondence between these 2 representations. We're going to see this frame diagram come back, so you'll get used to it as we go forward. Oops. Now, an important part of how data frames work is that they manage internal array stores called blocks. Block structure might deviate from the actual column presentation. So what you see when you're working with the data frame is not how the data is actually stored. And that's important because in consolidating same type data into fewer blocks, we get better performance. In essence, we can do more in NumPy, and that will give us better performance. So there's maybe 3 block consolidation strategies. We could have unconsolidated blocks, where each column is a one-dimensional array. Or we could have order-dependent block consolidation, where adjacent, same-typed columns can be consolidated into 2-dimensional blocks. Finally, we could have order-independent blocks, where all columns are consolidated into a 2D block per type. So I know that's a lot. So this diagram here should help you understand what we're talking about. So on the left-hand side, we have the represented values. Here you see a data frame that has a couple of columns of integers, booleans, and floats. You just see one type per column. But the blocks might be constructed differently. On the right-hand side, we see these 3 options where we have unconsolidated blocks, maybe one-dimensional array for each column. Order-dependent block consolidation combines adjacent columns into larger 2-dimensional arrays. Order-independent blocks disregards order and simply consolidates column data by type. So this block consolidation has trade-offs in terms of performance and complexity. So order-independent consolidation, as used by pandas, gives the opportunity for optimal type consolidation, but requires more complexity because we have to translate from those blocks to the representation that the user sees. Order-dependent consolidation, as used by StaticFrame, is suboptimal in some cases. We can't consolidate everything, but this gives us less complexity and, as we'll see later on, improves our serialization performance because we don't have to do that translation from the consolidated blocks. All right, I'm talking about complete data frame serialization, so we'll talk a little bit about what that is. Now, no legacy format except Pickle, supports all DataFrame characteristics, and I really mean all characteristics. So generally there's some sort of limits on the array data types. Like there may not be a perfect mapping of your array types into your serialization format. There's often limits, as we've already seen in Parquet, on what the types of the columns and index can be. And there's often very limited support for those name attributes, which, while not that important, can be really annoying to not have come back and forth from your serialization. Now, Pickle, in many cases, is the fastest at reading and writing data frames. We can always pickle a data frame in Pandas or StaticFrame, but Pickle is not really safe as a long-term store. As I hope all of you know, untrusted code can be executed in a Pickle. And Pickle is not suitable for long-term storage. A Pickle can hold on to references of objects that are no longer available, and you can end up pretty easily with broken Pickles. So complete DataFrame serialization needs to encode all the values and types and encode all index and columns labels. We need to support hierarchical labels. We need to support heterogeneous types per label depth, and we need to get those name attributes. So I want to make clear that Parquet is not a data frame. Parquet came out of the Apache Hadoop system and was designed for cross-platform, cross-language support. It is really a table implemented as unconsolidated columnar data. And it's great for that purpose. It has very sophisticated mechanisms for handling large data sets and rich metadata, but importantly, it's not a data frame. So we shouldn't be surprised that we lose information in translating back and forth to Parquet. So let's take a deep dive into NPY and the NPZ format. So the NPY format is a binary file format. What we have here is a header followed by a payload of contiguous bytes. Now, in order to translate contiguous bytes into an array, we need three things for NumPy. We need the dtype, which is going to tell us the bytes per element. We need the order. Is it Fortran, column major, or C, row major style, two-dimensional or larger array? And we need some specification of the shape of that data frame. So here's a little example. You can do this on your own of going back and forth between bytes. Here I have a simple 3-element array of Booleans, and I can call the toBytes method, which from any NumPy array will give me the contiguous byte representation behind that array. And I can translate that back into an array by using here the from_buffer constructor. I need to specify the dtype. We need to tell NumPy how to interpret those bytes, but as you can see, we get back the array that we started with. So back to NPY. So an NPY file consists of a header and a series of contiguous bytes. In the header, we have a number of things. We have what's called the magic prefix, which is a binary string that has a special binary character and NumPy right there, so you know what you're looking at. It has 2 bytes to provide the version number. And then it has the byte count of the remaining header, so that a consumer of this file knows how many bytes to read before we get to the contiguous byte data. The remaining header has a binary encoding of a 3-element Python dictionary. And that dictionary is going to tell us the dtype description string, whether it's Fortran order or C order, and the shape of the array. We're going to have a little bit of padding there so we can align at 64-byte divisions. So this diagram makes clear the structure of the NPY. We have the magic prefix in purple, we have the version number in green, and we have the padded header length, again telling us how far we need to read to get the rest of the header. The header here of the array is given in orange, and we see that's an encoding of a Python dictionary to tell us how to interpret that contiguous byte data. We have a little bit of padding, and then we have the contiguous byte data, which you should recognize now as that same Boolean array we started with, consisting of false, true, and true. Now, the original NPY implementation supports object arrays through pickling. But for our purposes, we're going to reject supporting object arrays and pickles in our data frames. Even if we just have only one array that's an object, any pickle compromises the safety and long-term storage of this format, so we're just not going to use it. And if you need to encode object arrays, you're better off just using pickle. Just pickle your data frame and you'll be fine. Now, I mentioned that NPY supports many versions. These versions aren't deprecated. They're a different kind of versioning system. So all versions are currently supported. And if you use np.save right now, it writes at the minimum version necessary. So very likely you'll get a version 1 NPY if you use this. These versions are differentiated by the available header size and the encoding, and versions 2 and 3 are really only there for structured arrays. We don't need structured arrays for what we're doing, so we can just stick with version 1. Now, I mentioned that this NEP1 defined NPY and NPZ. So what is the NPZ? Well, the NPZ is very simple. It's just a zip bundle of the NPY files. The original specification provides no standard naming or no metadata file. In my work here, that is what we have added. You can write these with np.savez, and we can read them with np.load. And if you do this, you get back a dict-like interface that allows you to get at your NPY files. Okay, so how do we encode a data frame as an NPZ? So what we're going to do is we're going to create an uncompressed zip. We're going to store all of our arrays as NPY files. We're going to store our values blocks as NPY files. We're going to store our index and columns labels as NPY files per depth. And we're going to use a common naming convention so we can find those NPY files. And we're going to define a custom JSON metadata file to give us all the additional information we need. So returning to the schematic that we started with, we can see how the components of the data frame are translated into the NPZ. We'll start with the orange and yellow values arrays. We see each of those becomes one NPY file to represent those arrays by type. We have 2 blue NPY files to represent the column data, 2 green NPYs to represent the index data, and finally, all the other stuff, the purple, is wrapped up in our JSON. If we were to look into some of those NPY files, this is what we would see. And hopefully this is familiar by now. We see a block 0 and blocks 1 represented, and we see that same header followed by a bunch of contiguous bytes. Now the JSON metadata file is there so that we can define the component types and additional metadata we need to recreate our data frame. We're going to define the component types as strings. We're going to define the depths as integers, which will allow us to discover our NPY files, and we're going to store the name attributes as a simple JSON array. So now we have the same diagram, but I'm showing you where we pull information into the metadata file. So in purple, you see that we have the name information gathered into a JSON array. We have type information stored in the green, yellow, and orange components of this little JSON object. And then finally, we have a depths JSON array that stores the depths of each of these components so we can unpack them later. So if you want to use this in StaticFrame, all you need to do is use our simple constructor and exporter. If you're bringing in an NPZ file, you can just say from NPZ, and if you're writing it out, you can just say to NPZ. As I mentioned, we spent a decent amount of time improving NPY performance. So, and the reason is because np.save and np.load are not designed for writing thousands or hundreds of thousands of NPY files, which is what we end up doing when we serialize a data frame this way. And NumPy's implementation priority is on compatibility. And what we found is a more narrow implementation can offer massive performance gains. So a couple things that we did to improve performance. We removed support for structured arrays. We don't need them, and this allows us to write version 1 NPY files in a very straightforward way. We also omit support for object arrays. A really important performance gain was achieved by removing backwards compatibility for NPYs authored in Python 2. NumPy does some tricky stuff in order to handle that situation, and we're just not going to support that. We also employ some header caching to improve the speed of translating that header into Python objects. In the context of encoding NPYs in a data frame, you're going to have a lot of headers that are the same. And so this cached header decoding really helps us improve our performance. Okay, so I've claimed that this format is faster than Parquet. We've seen a little bit of example, but let's dive into some greater details of this. So we're going to look at a number of benchmarks reading and writing data frames. And we're going to use pandas to read and write a data frame to Parquet. We're going to do it both with the snappy compression, which is the default in pandas, as well as no compression. And then we're going to use StaticFrame to read and write in both NPZ and pickle files. Pickle gives us another benchmark on the other end there. Now, of course, OS and hardware affect performance of file system operations like these, but I've tried this on a few OSs, and it seems to be pretty robust. Most importantly, shape and dtype heterogeneity matter. Too often, I see performance benchmarks of data frames where they just have done something with one data frame, but the shape of the data frame and the underlying dtype heterogeneity really matter. So we're going to look at performance across 1 million elements and 100 million elements in various shapes and dtype configurations. And I generated those values using a package called frame fixtures, which allows me to easily generate a variety of frames. So we're going to explore 3 shape ratios. So the shape matters in how a data frame can perform. We're going to look at tall shapes, square shapes, and wide shapes. And we're going to look at 3 types of d-type heterogeneity. We're going to look at columnar, where we have 1 d-type per column with no block consolidation, mixed d-type heterogeneity, we have 2 pairs out of 5 that are consolidated, and uniform d-type heterogeneity, where we have 1 block that can represent all of the data. So when I present these 9 benchmarks, we're going to see them in this presentation. So I just want you to get a sense of it before you see all these graphs. We're going to have the shape variations across the columns, tall, square, and wide, and we're going to have the d-type heterogeneity along the rows, columnar, mixed, and uniform. Okay, so let's look at read performance. I know there's a lot of information here, so I'll try to help you out with it. In dark blue, we have Parquet with compression. In purple, we have Parquet without compression. In magenta, we have NPZ. And in orange, we have Pickle. So we see right away that Pickle's very fast. Okay, that's our first observation. Notice that NPZ in magenta is faster than Parquet with and without compression in all cases here. And as the data gets more uniform, as we go down, we see that NPZ performance increases. Notice also that with the compression sometimes reduces Parquet performance. That's going to be relevant when we look at the trade-off in sizes, in file size on disk. Now, if I scale this to 100 million elements and we do the same examination, we see the outperformance of NPZ continues. And we see now that the compressed Parquet always underperforms the uncompressed Parquet. And I want you to keep that in mind when we look at file sizes. There's one case where that's not true. But notice again here, lower is better in all these graphs, that NPZ in magenta is significantly outperforming reading Parquet. Now what about writing? Well, here NPZ does really well. We see again in magenta, NPZ, that bar is always lower than Parquet. And again, lower is better here. And we see NPZ writing, in a few cases, even outperform Pickle, those tiny little lines there at the bottom. So this is a really exciting observation. And this similarly scales to 100 million elements, where again, NPZ, again in magenta, lower is better, continuously outperforms Parquet in writing out complete data frames. So what about file size? Well, we have to consider compression when we consider file size. Parquet supports many types of compressions, and that's a really fantastic feature of Parquet. At this point, we're not doing any compression on our NPYs, and we're not even using compressed zips because that degrades our performance. Even without any compression, NPZ size compares favorably, which is very interesting. NPZ is always smaller than Parquet without compression, but when NPZ is larger, it's generally not more than 25% larger than Parquet with compression. Okay, so here's a similar chart of the resultant file size on disk of NPZ, Parquet, and Pickle. Again, Parquet is in dark blue with compression, purple without compression. And right away, we see that the compression works. Compression is always smaller. Notice also the NPZ in magenta is sometimes always smaller than uncompressed, sometimes even smaller than the compressed Parquet. And that's a really interesting observation. Now, as we scale this to 100 million elements, we see the benefit of Parquet compression. Now, compressed Parquet files are always smaller than the corresponding NPZ file, but the NPZ file is still always smaller than the uncompressed Parquet. Now, we do get a smaller file size with Parquet, but if you remember our performance numbers, the compressed Parquet read-write performance performed very poorly at this scale. So there's trade-offs in compression, as I'm sure you're aware. Now, what about memory mapping these data frames? So a memory map is a segment of virtual memory assigned a byte-for-byte correlation to the bytes in a file. And for large files, this can increase read performance significantly and can permit an incremental, lazy loading of data into RAM. So how do we memory map an array? Just if we have an array, what can we do? Well, we can use the standard library's mmap to create an instance from the bytes in the body of the NPY file. And then we can simply hand that mmap to an ND-array constructor as the data buffer for the array. So let's do that. We're going to create a simple binary file, and we're going to put the 3 bytes that hopefully you know by now into that file. We're going to open that file back up as binary. We're going to give it to our memory map, and that's all we need to do. We can create an ND array with that memory map as the buffer, and we have a memory mapped array. So we can do that with our NPYs, but we can't use a zip anymore. What we need to do is write all of our NPYs to the file system, and StaticFrame offers an exporter to do that. You simply say to NPY. We're going to give it a directory, and we're going to fill that directory with NPY files. To get the memory mapped file back into memory, we're going to use a specialized constructor that's going to give us back two things. It's going to give us back a frame and a special function we need to close the memory maps after we're done with them. So this gives us some overhead in working with memory map data frames. We have to lay out everything on the file system. And we must remember to close those memory maps. But even so, we can get even better performance. So NPY at the scale of 100 million elements always outperforms NPZ. And we see, well, it just drops off the chart here, outperforming Pickle itself in reading in a data frame, which is a very exciting result. So memory mapping a data frame provides significant benefits in read performance, often being faster than NPZ, maybe always, and offering better memory performance. And this is really enabled by StaticFrame, in part because the NPY structure is identical to the blocks, and those blocks are adjacently consolidated, meaning we don't have to do any translation to get at that underlying data. Furthermore, unlike pandas, StaticFrame has an immutable data model, and because it's a mutable data model, we can memory map all of that array data into our frame, and we can take views of that memory map data without forcing premature copies, which means we can keep our memory map data and use it for quite a long time before having to make any copies. All right, current state and future work. These NPY, NPZ read-write routines are fully implemented in StaticFrame. We're already widely using them in production and have observed very significant performance benefits converting from using Parquet to using NPY and NPZ. As mentioned, you can export and import these NPZs with constructors and exporters with names that should be familiar to you. If you want to go to an NPY, a directory of all of this data, there's similar exporters and constructors. And finally, we saw the special NPY mmap constructor that allows you to memory map a complete NPY from NPYs on your file system. If you're using pandas, you can use this right away. You can simply convert from pandas to StaticFrame, write out your NPZ, or do the same in reverse. Use StaticFrame to read your NPZ and then convert it to pandas. Now, pandas has drifted away from NumPy a little bit, so if you're using pandas DataFrame features that aren't part of NumPy, you're not going to be able to do this. But if for very common NumPy dtypes, this will work perfectly well. In the future, there's a few more optimizations we have to explore to further increase the performance of reading and writing these NPY and NPZ files. And we might explore NPY compression. As we saw, the benefits of compression for very large data frames is potentially valuable. All right, so I hope you've gained a good understanding of data frames and how they are built. I hope now you have a clear understanding of how this 14-year-old encoding mechanism works and how we can redeploy it now to produce something that's actually materially faster than the so-called gold standard of data encoding. And I hope you leave here with more options for serializing and, in fact, memory mapping data frames than you had when you started. Thank you very much. If you'd like to learn more about StaticFrame, you can visit us here. Thank you.